Hello, everybody. I'm Fiona Trahe. This is Paul Luse from the storage group in Intel, and we want to talk about using DPDK for storage, for compression. So we're going to break this into two parts. First of all, I'm going to talk a little bit about compressdev, which is the new API that we added to the storage, which we added to DPDK. And then we added some pull mode drivers, and we're now moving to the next layer up. So we want people to use that, and the storage group are integrating it into SPDK. So I'll talk a little bit about DPDK, and then I'll hand over to Paul. Okay, so this is just giving an overview of DPDK in general, and you're all pretty familiar with that, I'm sure. It's all of the libraries. The top layer is the general libraries that are used by lots of applications and as infrastructure. Particularly the ones on the left are the most interesting one, the core libraries that are used for memory management, bus device management, PCI management, that kind of thing. So in 1805, we added a compressdev library. This is along the second layer. You can see ethdev was always there, obviously, and then cryptodev was added, and a bunch of other APIs. So we added compression, and we modeled it on cryptodev. So we kind of took that as our baseline, and then we put in a separate API, and that allowed us to change things a little bit, and it was actually quite useful to do that. So compressdev is, you'll see a little bit later, the similarities with cryptodev, if you're familiar with that, and then some of the things that we did a little bit differently. And then we also, so all of these APIs are for allowing you access to devices, both software and hardware. And so we added some pull mode drivers underneath compressdev. Okay, so just talking about compressdev itself and the features that we have in there. Our main purpose, I guess, in adding compression device was so that you could use a compression engine, either hardware or software. Software wouldn't really care if it was asynchronous or a burst API, but for optimizing hardware, you'd like it to be an asynchronous burst API. So we followed the same model of cryptodev and ethdev for that. And obviously, by having an asynchronous API, that allows you to hand over an operation to a hardware device, an engine, and then go away, do some other work, use that cycles that you've saved, and then come back and retrieve the results when they're ready. So mbuffs are the standard mechanism for passing data around in DPDK. They're not necessarily hugely advantageous for compression. For storage, they're more aligned for networking, which compression can be used for both of those, for both the storage and the networking areas. So we have stuck with using mbuffs. We have investigated some other alternatives, but for the moment we're using mbuffs. But it's really important in compression in storage that the data is not necessarily in one contiguous buffer. So you may have multiple buffers, and they may also be external. So the new feature of attaching external buffers to mbuffs has been quite useful, and that's what Paul is integrating at the moment. And so having a chain of mbuffs that are in the memory domain of the application is quite useful. The algorithms that we support are deflate and LZS. Deflate is the name of an algorithm, in case that's not clear to people who aren't familiar with compression. And it's the standard one that's used in storage. LZS is more commonly used with IP-comp in networking. So in terms of levels, you can compress the different levels. I'm sure you're all well aware with things like zlib. That you can compress many, you have a trade-off. You can either get a better ratio, which takes a lot more processing power, or you can get less of a good compression ratio, but and do it faster. So we have 9 levels available. We know that every underlying engine doesn't necessarily support 9 levels, so it's up to the PMDs to map from the 1 to 9 levels to whatever levels they can support. But on the API, we expose 9 levels. And the last 2 things that you'll see on the slides are about authenticating the data. So checksums and SHA, you can do a hash generation on your uncompressed data. Okay, so this is just an overview of the whole infrastructure of compressdev. You've got your typical application outside of the DPDK domain, and then within DPDK, you've got a bunch of APIs in the API layer. The ones that you'll see on probably should be pointing at this rather than here. The standard ones that are the same are similar to ethdev or cryptodev would be your device management, find the device, find some queue pairs, expose those queue pairs, and set up the device so you can use it for your service. Then the data path in queue and DQ is also your standard burst and queue, burst DQ. And operation management, you typically build an operation, build multiple operations, and send them all in a burst onto the device. The things that are a little bit different are the stream management. So if you're familiar with cryptodev, there's a concept of a session, and that session allows you to set up data that's immutable across many operations. So you take your data, send it off to the device, get it to set it up, and then attach that session to every operation afterwards. We didn't find that session concept quite fitted compression, so we've got something called a stream or a private transform. They're two different structures that we've provided, and those structures allow you, this is the same kind of idea. You're passing down some configuration to the device through the API, it gets set up, and then you can attach that session, or that private transform or stream to every operation. So, yeah, so that's where we deviated a little bit from, quite a lot from compressdev. The last thing is capabilities, and capabilities are, I guess, they're common for a lot of for compressdev and compressdev, and it's really important because devices, hardware and software, have different capabilities. In this case, particularly, we have stateful and stateless compression. Not all devices will be able to support both of those modes of compression. So, capability API is quite useful to figure out what you can support. Okay. All right, so I'm just going to walk through just for a little bit of terminology around compression, and just to make clear some of the details around SGLs and the idea of stateless operation versus stateful operation. So on the slide, what you're seeing is two different chunks of data that need to be compressed. So the first chunk might be in multiple buffers, so I've got 4 buffers here. Those 4 buffers are all attached to 4 different MBuffs chained together, and then you can pass them down through your compression engine to your compression engine through the API. What you get out of the compression is not, the number of buffers they're in is not related to the number of buffers you passed in. So in this case, I'm showing that they come out as 2 buffers with compressed data. And this size, which is illustrated on the slide, when you see that when you compress the data, it's smaller, obviously, than it was passing in. So that changes the nature of what we have to do in compression versus what we did in compressdev. In compressdev, your input size is always identical to your output size. So you can, for example, have in-place operations where you take your data and you have the same space for the output data. This is different. So we always have out-of-place operations for compression. And when you decompress the data, when you decompress it, again, it can come out into whatever buffers you provide for it. They're the buffers that it'll end up in. So in this case, we're seeing the first operation, when you decompress it, you end up with, if you've passed it 3 buffers, then the data will end up in 3 buffers. It's not related to the number of SGLs that are on the chain going in. So there are just some interesting kind of different semantics from compression versus crypto. Okay, so I'm going to pass you over now to Paul. Actually, there's some links here you can look afterwards on the webpage and find out a bit more about compression if you want to. I'm going to pass you over to Paul now, and he's going to talk about SPDK and how we integrate it, how we're in the process of integrating it.
Excellent. How do I make this thing go forward?
Just press the green button.
Press the green button. All right, I can do that. Well, everybody, thanks, Fiona. My name is Paul Luse. I am a proud member of the SPDK community, and I also happen to work for Intel. How many folks, show of hands, have heard of SPDK? All right, that's pretty good. Okay, now, how many folks consider themselves storage experts? Awesome. I can make shit up, and you guys will have no idea what I'm talking about. So let's get started. Okay, so what is SPDK? It's the Storage Performance Development Kit. Sort of familiar acronym there, the way it's being used. We are also fully open source. We're also a set of libraries and also applications that storage developers, storage companies use to accelerate performance in their applications, right? For all the same reasons that networking folks use DPDK. Right, so we have pulled mode drivers, we have lower latency, we have higher throughput, right? All the same goodness of DPDK. We're also all BSD licensed. We've been using DPDK, I think, for about 5 years, primarily for environment abstraction, and you'll see that on an upcoming slide. And then this year we've started using DPDK for a bunch of other stuff, and that's one of them is obviously compressdev, which is why I'm here. I can't talk about SPDK without talking a little bit about our community. Like I said, I'm a proud member of this community. We're 5 years old. We started off really as a science project in a lab at Intel, a really small team of people, all closed source, just trying to experiment and see how we could get NVMe Express drives to go faster, right? And hopefully everybody knows what an NVMe Express drive is. I know it's not a storage crowd, but right, NVMe Express, awesome protocol for super fast SSDs. So NVMe Express suffered the same problems that a lot of the networking side had with the drives being faster and not really being completely utilized or completely leveraged by the applications because of the OS getting in the way. So this, like I said, this started 5 years ago. Just a couple people experimenting and discovered, hey, if we write a user space pulled mode NVMe Express driver, we can really get these things to smoke a lot faster than you can going through the OS. So that over time grew into what we are today, and really over the last year and a half is where we've made really the significant growth in our community. We've got all the big storage companies are involved. Everybody's using SPDK for something. And what we're really proud of is everything we do is completely open. We're a completely transparent, completely interactive community, just like the DPDK folks. What I've got on the slide here, I'm not going to go over all these, but just shows you our different tools and our different communications channels, our different mechanisms that we use. We've got multiple meetings every week. We've just got a great system, and everybody that participates just constantly gives us positive feedback on how easy it is to get involved with the community and to leverage our code and to contribute patches. Okay, so let's talk a little bit about how SPDK is using DPDK and a little bit about what it is. Now, our architecture slide has about 50 things that I didn't include on here, primarily because you guys are not a storage audience, and it also makes the slide extremely busy and could take probably a half hour just to explain what SPDK is, because it is really deep and it is really wide. As I said, it's not only libraries that applications can include to use our pulled mode drivers and a whole bunch of other services, but it's also actual binaries that people can use, right? So as an example, in the upper left here, you'll see NVMe over Fabric's target. So that's actually a binary that they can load on a system and use that box as an RDMA target for NVMe Express, so that some other initiator, right, in some other box somewhere can treat that as an NVMe Express drive. So you wouldn't even need to integrate your application to that. So we've got a couple of examples of that, but that's the one that I've got on here. Currently it's RDMA focused, and we also have TCP that actually was just released. I think it says under development, but it was just released. So we do have TCP as a transport as well. So like I said, we get a bunch of other stuff, but at the top there, we just call that sort of our applications or our storage interface. This is where people are coming into the box. Now, the middle layer is where I really removed a lot of the busyness, to really focus in on what we're talking about here. But the middle layer is what we call our BDEV layer, or the best way to think of it is a user space storage stack, right? It kind of mimics a lot of the stuff that you would see in a storage stack, either in Windows or in Linux. One of the key components is the block device abstraction, right? So we'll take a disk drive, right, and you make a generic block device abstraction out of it, and we use our own API at the top end. So we invent, an API to say read, write, open, close, all that kind of fun stuff to a block device. And then at the bottom end, we go out to our pulled mode device drivers, and I'm showing the NVMe Express driver here as our most robust pulled mode driver and the easiest one to understand. Out that back end, we've got a shim that converts our API, the BDEV API, into the NVMe Express API. So what this buys us by putting this device abstraction layer in is the ability to slip in other modules, kind of like a filter driver concept on the Windows side. You can slip in another module and sort of stack them. So you can have one module that is a BDEV that represents an NVMe Express device, and you can put another BDEV on top of it where the IOs flow through these vertically and do something to the data, right? You can transform the data on the way in, and you can interrupt on the way out and transform the completion. So it gives us a lot of flexibility, and a lot of storage customers appreciate the ability to add their IP to the storage stack without necessarily having to open source that particular component. So when you stack these things together, we call them virtual BDEVs. And that's how we have implemented the compressdev API into the storage stack. So this would be our virtual BDEV here. I think I can see this. My eyes aren't good enough to see this whole thing. I've got a better slide coming up, but so we've got a compressdev virtual BDEV that intercepts IOs on the way in, and then it goes out and talks to the DPDK API, compressdev, does the compression, decompression, sends the compressed data down to the disk, and then on the way back up, it is the exact same thing, right? It intercepts compressed data, sends that data stream over to the compressdev API, uncompresses it, and then sends it back up the application, right? So it just gets in the middle and does cool stuff. I said there's like at least 15 or 20 other things that I could have on this slide, but off to the right, you can see really the primary purpose that DPDK has served for SPDK for quite some time is through the environment abstraction. And we actually have abstracted that as well into this env.h file that allows some customers that aren't using DPDK to potentially use their own applications or their own environment framework if they already have it. Okay, so creating a compression device in SPDK. So this is probably a little better picture to explain what I was talking about with the virtual BDEV concept. If you look at the left-hand side of the slide, you've got the application, and this is local. You've got the application coming into the BDEV layer, and then immediately going into the compression VBDEV. And then the compression VBDEV actually has two other interfaces that it talks to. Now, when you talk about doing this on a storage device, compression decompression is a little more complicated than crypto. And I'll talk about crypto here in a second, because we also did that last quarter. But when you compress and decompress data, obviously the size of the data on disk changes. So we, as the storage application, have to remember and keep in metadata where all this stuff is at, right? As physically on disk compared to logically where the applications think it is. And in order to do that, our metadata operations need to be really quick, right? Because we're going to do a lot of them, and they're fairly small. How many folks have heard of persistent memory? Right, byte addressable non-volatile memory. So persistent memory out of the SNIA twig has got a specification, and one thing that rolled out of that specification, also fired up by Intel, was the PMDK, or the Persistent Memory Development Kit. And that provides a fairly easy way for applications to use persistent memory. So you can see above our VBDEV, we've got PMDK in there. We're using persistent memory to store all of our metadata. And one of the primary reasons why, besides speed, is that it's byte addressable, right? So in the storage world, when you want to do a read or a write to a disk, the smallest level of granularity you can do is a block. And a block can be anywhere from 512 bytes. That's sort of older technology. Most of them are 4K. But if you need to update like 64 bytes of metadata on a block that's 4K, you have to read that 4K in first, modify the 64 bytes you want to modify, and then write it out again, right? I mean, read, modify, write. That's incredibly inefficient and slows the whole thing down. So with byte addressable memory, we only have to target the metadata that we want to update. So not only is the media fast and the interface fast, but it's byte addressable. So that's where you see the picture there between PMDK and the reduce lib talking up to the non-volatile memory there. Now, reduce lib is another library that we've had to develop in order to implement compressdev, and it's managing really the placement of the metadata and the understanding of when the I/O operations are happening where. So in the virtual BDEV itself is sort of like the traffic cop. Right? An I/O comes in from the application, goes to the virtual BDEV, says, I need to read, block 56. But the application has no idea where that's on disk or how big it is, right? The only one that knows that is the reduce lib. So the virtual BDEV will call into the reduce lib and say, hey, I need block 56. And he's provided some function pointers in advance to reduce lib, who then does all the math, reads up the metadata, decides where the real data is and how big it is, and that call goes back to the virtual BDEV, which goes down our stack out to the BDEV, if it's direct access to the disk, and then down through a pulp mode driver, and you can see over to an SSD. Now, if it's compressing or decompressing the data as opposed to just reading and writing raw data for reduce lib to consume, that's when it takes this path off to the right and goes through the compressdev API. Now, our initial release of the compressdev is going to support two PMDs on the DPDK side. One of them is the ISA-L PMD. Anybody heard of ISA-L? Awesome. That's also out of my team, as well as SPDK. So we've got the ISA-L guys in the same lab. So ISA-L has a PMD in DPDK. So we've got that one up and running already. Not completely ready to go yet. We'll be releasing this probably in the first quarter of next year. And we'll also be supporting the hardware acceleration with the Intel QAT card. Okay, so hopefully that makes sense. Any questions on this so far? Okay, that's good. Okay, so let's talk about The predecessor to this, what we did with the crypto module, which we just released last quarter, it's very similar, and I don't think anybody appreciates the similarity between the compressdev API and the compressdev API more than I do, because I had to write both of these. The compressdev module was pretty easy to get, or the compressiondev VBDev module was pretty easy to get fired up and running because it was so similar to the cryptodev. The cryptodev is actually more of a simplified model because we don't have to deal with metadata, right? Because the size of the data on disk and the location of the data on disk doesn't change with every operation. So if the application says, I'm writing to block 100, it's going to be at block 100. We're not doing any fancy translation, or the size doesn't change, like I said. So it's pretty basic. It comes into the virtual BDev. We get the data on the way in. We fire a API off over to the cryptodev. It does the compression for us. We provide the buffer where we want it encrypted. When we get that completion asynchronously, we send that down to the disk through the same kind of path that we just covered on the compressdev API. And then the same thing on the read side, right? When an application comes in and says, I need some data off disk, it doesn't even know it's encrypted. Well, it knows, but it doesn't have to worry about it. It goes to the virtual BDev, and the virtual BDev says, oh, I'm going to read the data off disk first. As soon as I have that in a local buffer, I'll send that over to the cryptodev API, do the unencryption, and then provide the unencrypted data back to the application. Okay, so we've got, again, more information both on SPDK. If you're interested in learning more about SPDK itself or getting involved with the community, all that stuff's on our first link there, spdk.io. There's also additional information here on PMDK. I did a talk earlier this year on PMDK and SPDK and how they work together and how they're similar and how they're different. I should have thrown DPDK in there too, just to have alphabet soup of project acronyms. And a bunch of other stuff on here too. So I think we've still got a good amount of time for questions. I know this isn't a prime topic for this group, so hopefully we've got some questions. We'll open it up now, either for Fiona or myself.
Just before you do go to questions, I guess there's two things I wanted to say. One was just the earlier slide you talked about with the environment that SPDK uses. I think it's worth us in DPDK considering, because I've just experienced the use of Gerrit Hub and GitHub externally. So Gerrit Hub is used externally in the community rather than a mailing list to do your code reviews.
Right.
And I'm experiencing that in action, and the use of IRC, which Thomas was asking us about this morning and saying we should all use more. In SPDK, they really model that. They're using, everything they do is done in public, in IRC. There's a constant chat going on in that window, and their patches are pushed into GitHub, into Gerrit Hub first. People review them in Gerrit rather than on a mailing list. And for me, I think that works very well for SPDK anyway. It's something we should probably consider a little bit. So if you want to talk about that, Paul's probably a good guy to get experience on how that works in an open source community.
We'd love to help out in those areas. Yeah, like I said, we're really proud of our infrastructure, both our CI testing infrastructure, our review infrastructure. We get positive comments all the time. People come in and say, wow, it's just so easy to interact with this community. And it wasn't easy to get it all set up, but it's very easy to use. It's very developer friendly. So yeah, absolutely. If anybody on the DPDK team wants to, talk about implementing some of this stuff, we're happy to do it as well. Right? IRC is another huge one. When we first started that, we had a few developers thinking, geez, nobody's ever going to use this. This is big waste. We should just stick with email. But after a couple of months, people started to realize, hey, I can ask a question and get an immediate response. And we've got core maintainers both in China, Japan, Poland, and the US. So we kind of have somebody covered in IRC all the time. And we've sort of, as developers in the community, have developed work habits that IRC is always open. You're always sort of glancing over and seeing what's going on and chiming in on real-time conversations. And that's been a really big hit for us. Another thing, I didn't mention it when I hit the slide, but we use something called Trello. I don't know if anybody's ever heard of Trello, but it's a completely open, public, anybody can go up and sign up and use it. It's basically a project management / collaboration system. We use it for all sorts of stuff. One of the big uses that we have for it that you might find useful for the DPDK community is solving the problem of new developers coming in and not really knowing, what can I do to add value? What can I do? How can I contribute? I don't know what to work on. So we've got our Trello board is categorized by the different projects within SPDK, by the different modules. And then when you drill into that, we have a whole list of like low-hanging fruit, right? Really easy stuff that somebody, that nobody's gotten around to, right? Somebody go and replace all these with whatever. And it's really allowed developers to come in and find something of value to do, whether it's adding a unit test or doing some basic refactoring, whatever. Then we've got another column for sort of medium level work and then kind of hard work. We also use it for setting agendas for our community meetings. We just use it for all sorts of stuff. It's so easy to use. That's just another one of the really big, the big winners that we found in putting together tools and channels for communications with our worldwide audience.
Any questions?
Can you go back one slide, please?
Hopefully.
So that red arrow implies there's a DPDK app working independently of the application.
So DPDK is linked from SPDK, and they're both independent of the application, but the whole lot are built into one.
In one application.
Yeah.
Right, yeah, this is one big DPDK application.
Does it mean that you just support one application per hardware, per crypto hardware? Because how do you share the crypto
One
hardware?
application per what?
Per hardware.
So if you're talking about Quick Assist in particular, I don't know about the SDs, I'll let you talk about, but if it was Quick Assist, for example, we would have multiple VFs, and you can have one VF per process. So one particular physical function will have multiple VFs, and you can, in particular, one of our devices, Lewisburg, has 48 VFs. That means you could have 48 separate processes. How you cut up the SSD, I don't know. Is that?
The way we do it in SPDK, this is one of those components I didn't list on our architecture slide because it's not super relevant to what we're talking about today. But we have kind of the equivalent of a volume manager in user space. We call it LVOL, or logical volumes. So what we do is it's implemented as a virtual block device, the same way that CryptoDev is, or compressdev, or any of our other cool value-added features. It takes an SSD and lets you carve it up into smaller virtual BDEVs that can be presented to different virtual machines or different applications. Well, it would actually be different virtual machines, and really allow you to carve up an SSD without having to worry about virtual function support.
Thank you.
We've got a few different ways of doing it, but that's definitely the main one, and that's the main use case we see for compressdev and crypto for both these virtual BDEVs. There'll be people putting them on top of LVOLs, which are carved up SSDs. It's a good question. Thanks.
Any other questions?
I have a question. See, if I am using hardware acceleration and I want to do compression and encryption, can I do it in a single pass?
No, not at the moment. So maybe in a single pass in terms of the application call in, because you could put two VBDEVs. It's not a case we don't, but certainly it would be at the interface between SPDK and DPDK, it would be two separate API calls sequentially.
Right, and yeah, so there's kind of two ways to answer it, right? The DPDK side and the SPDK side, and I think they're both the same answer.
Okay.
No, right? The way you would do it in SPDK is, remember I said you can stack these virtual block devices. You would stack a compression one, a crypto one, and then an SSD one on top of each other. But it would be multiple calls and multiple passes. So the data would be passed through one virtual BDEV, going over and be compressed or encrypted, come back, pass to the next virtual BDEV, who has really no knowledge of what's above him or below him other than a standard API. He'd go do the other operation and pass it down or pass it up and so forth. So you could do it, but it wouldn't be one pass to the hardware offload. It'd be two.
So if I have those two accelerators in a smart NIC, then do I have to do memory copy twice? So do the compression and get the data into the host memory, and again send it to the accelerator to do the encryption, and then again send it back to the host memory?
So we haven't integrated that case, but I would think in both in the compression one, we're trying to avoid copies of the data. So the application data, the buffers that's in, that'll get passed in to the compression engine, for example, in the compressed case, and come back out into other buffers. So you avoid a copy on the first part. The data you get back then is in new buffers, and then that would have to be, those buffers would then be encrypted. So again, you wouldn't have to copy them into something else to do that encryption call. Or even if it went back to the application, if if it was two calls, the buffers that you got back, you could pass the same buffer. So they're buffers attached to an MBUF, and generally they're not going to be copied. The only copy we have at the moment really is when the compression engine, compresses and outputs the data. It's output into a different buffer, so that buffer may have to get, transferred usually onto disk.
Thank you.
Okay.
Yep, thanks. Another good question. You guys are more storage focused than I thought.
Okay.
Excellent.
I think we're probably out of
Okay.
time. Just maybe one more call. This is very much work in progress. So if anyone, we'd really appreciate feedback from anyone who has any storage interest to come and talk to us. We'll be around here for the rest of the day. So
Yep.
give me a shout, and we'd love to hear your feedback on it.
Yeah, the crypto stuff is released in SPDK, and the compressdev stuff, like I said, will probably be early Q1. It'll be ready.
Okay.
All right, thank you.
Thank you.
Thank you.